Hi, welcome to the final module in ABS 470. So this is module 7. You have made it. Professor Jared Rathel here, and today I'll be focused on mammalian population dynamics and life history traits. I have to admit, this is a topic that has absolutely fascinated me for over 20 years of my life. This is a photo many moons ago of me in my mid-20s, and I've just placed a mortality sensing radio ear tag transmitter on a newborn calf elk. So this is the calf after it's been radio marked before the bear, and then here's that same calf a few days later after the bear. So lecture 7.1 is going to align with chapter 25 in your textbook. And more importantly, this lecture is going to prepare you for your final case study, which explores the population dynamics of the Rocky Mountain elk. Specifically, I'll highlight research that we did in the early 2000s that documented just how extremely variable neonatal elk survival, meaning newborn calf elk survival, can be over time within a population and across space from population to population. Ultimately, there's a lot of serendipity. There's a lot of luck in wildlife research. So we just happen to be in the right place at the right time, radio marking these newborn calves. But I'm not going to give the whole story away here on the first slide. That's my cliffhanger, my trailer to keep you engaged. There's more coming soon to a theater near you. As always, we'll begin with some basic terminology. So today we're focused on the population, so this biological level of organization. Last module, when we talked about interspecific interactions, things like predation, mutualism, at that point we were working at the community ecology level. Today we're going to put on our population ecologist hats. Population, of course, is just a group of individuals of the same species that occupy the same place at the same time. And we recall from our general biology class that two individuals are considered the same species when they're capable of interbreeding and producing viable, fertile offspring. That's the biological species concept. So as we think about population abundance herein, population abundance is just the size of the population, or population density, which is the number of organisms per some unit area. When we think about how abundance and density changes over time and or across space, we recognize that population dynamics all rests on this fundamental equation known as the Bide balance model. So population abundance, which is N, at time step t plus 1, so that is to say one time step from where we're at now, is equal to the population abundance at time t, at the time it is now, plus births, okay, or natality, and immigration with an I. So births and immigration represent deposits in the population bank account, if you will, minus deaths, D, and E, which is immigration. So these are individuals that permanently leave the population. Okay, so population abundance, one time step forward, is the current abundance plus births and immigration minus deaths and immigration. So what other inherent characteristics of the population should we consider? Well, age structure and sex ratios are a very good place to start, as these vital rates can dramatically impact mammalian population dynamics. By age structure, I just mean the proportion of individuals in each age class. And an age class is just a generalized grouping of individuals based on their ages according to similarities in their survival and or fecundity. So regardless of mammalian species, age classes are going to look like usually neonates, newborn, juveniles, sometimes subadults, adults, maybe prime-aged adults, maybe senescent adults. So a good example of age classes, these are the ones that I selected for the second chapter of my thesis when I did a meta-analysis. So I looked at data from 40 different elk herds from different times and different places. And based on the distribution of these data, I broke out the elk age classes as such. Calves. So this is the time period, the neonatal period when they're first born, as well as the juvenile period up until their first birthday. So from 0 to 1, we refer to them as calves. From their first to their second birthday, we call them yearlings. And notice when they become yearlings, now they have a fecundity contribution. Okay, so now we're going to produce calves. Prime-aged adult elk are from 2 to 10 years old. Old-age elk from 10 to 15. And then we had some long-lived collared elk, including one that was over 20 years old. Anybody over 15 was lumped into the senescent adult age class. But the point is that these age classes had dramatically different vital rates. So, for example, pregnancy rates, which is the main component here in this fecundity rate. The pregnancy rate of yearlings was only about 50%. Only about half of the yearlings became pregnant, whereas the pregnancy rate of the prime-aged adult females was 92%. So it made sense to split these groups out according to age class. Sex ratios are also very important. That's the proportion of males to females within the herd. We really focus on females when we're thinking about population ecology because females are the ones with the reproductive potential. They're the ones that are contributing to population growth. If you remember my case study on black bears, we built female-only black bear matrix population models. So sex ratios can certainly vary among age classes, particularly in polygynous species. You will recall that polygyny is when we have one male and multiple breeding females in a harem. So we can see skewed sex ratios in polygynous species and also in harvested species. So for example, when I would do the aerial survey flights for these elk, which I did regularly for 3 years, I would often count maybe 3 to 5 prime-aged, mature, branch-antlered bulls for every 100 cow elk. So I'll come back to it, but this was worrisome to us. We wondered how this lack of mature bulls, the ramifications of these highly skewed sex ratios might be impacting calf survival, and I'll come back to that. And then finally, probably the most important metric, at least with respect to elk, is recruitment. And recruitment is the number of juveniles that survive and become recruited into the reproductive, the breeding portion of the population. So when an elk calf survives that first year and becomes a yearling, it then has the potential to breed and produce calves of its own. It's considered recruited. And so different species, it doesn't have to be a full year, different species with faster tempos, right, may be recruited into the breeding adult component of the population more quickly because their time to maturity is much smaller. So think about rodents. So rats can become reproductively mature in just 8 weeks. Mammals, like all species, are going to exhibit patterns in their survivorship, which are often represented graphically by the 3 types of generalized survivorship curves. So these are showing the pattern of mortality across the organism's lifespan from one age class to the next. X-axis is lifespan, so here's pre-reproductive, the dependency period, these are the young and the juveniles. Here is the adult period and the post-reproductive or senescent period. So this is the Wrathel age class here on the far right. The Y-axis is just survival, and then it's been normalized on a log scale. So there's 3 types of survivorship curves. Type 1, right here, illustrates relatively high survival of young, high survival of reproductively aged adults, and then high survival of the senescent adults until you hit the end of the lifespan, and then mortality dramatically increases and log survivorship dramatically decreases. So this is clearly us, right? So the majority of our infants and children survive. There is a little dip in survivorship during those teenage years, particularly in males when they they can be very wild drivers. But we tend to survive across our adult years, and then we hit our late 70s into our 80s and fall off really rapidly. This is also whales, elephants, so most large mammals show a type 1 survivorship curve, whereas small mammals, so think squirrels, rodents like this white-footed mouse here in the genus Peromyscus, they're going to show a type 2 survivorship curve, which is mortality rates that are more or less constant across the lifespan, across all the different age classes. The slope is the same. It's a linear model here. Okay, so your chance of surviving is pretty much the same at all of these different periods throughout your lifespan. And then a type 3 survivorship curve shown right here. This is when mortality rates are highest in the young, the early stages of development. So type 3 survivorship curves are really characteristic of invertebrates. So this is a wolf spider with her spiderlings riding around on her back. The vast majority of those baby spiders are not going to survive. It's the same with the oak tree. Think about the thousands of acorns that are produced by an oak tree in any given year. Only a minute proportion of those acorns are actually going to germinate and then grow into a reproductively aged adult oak. So type 3 survivorship is rarely seen in mammals because of the large investment female mammals make in their offspring via gestation and lactation. Recall that this high parental investment in our young is one of those defining mammalian characteristics. In the next case study, you're going to hear me talk about lambda ad nauseum. So let's make sure that we've got our heads wrapped around this. So lambda refers to the per capita population growth rate. It's also called the finite rate of population growth because lambda refers to the change in population abundance over one discrete time step. So it's finite. That time step is usually estimated in years but other time steps may be more appropriate depending upon the species. So perhaps you're looking at changes in population abundance in a cyclic species like the brown lemming in Barrow, Alaska. So then you may be interested in peak population abundance, which occurs every 4 years. So in that case, a longer time step may be more appropriate, or if you have a very fast tempo species, perhaps a shorter time step. So ultimately, though, it's pretty easy to see what's going on with lambda. So lambda is just a function of population abundance n at time step t plus 1, the next time step, relative to the original population abundance. So if lambda is greater than 1, that means the population is increasing. If lambda is 1, that means the population is stable, and the population abundance, the numerator here, was equal to the denominator. This number divided by this number equals 1. And then if lambda is less than 1, it means the population is declining. The other thing with lambda, it's really easy to just convert it to a percentage. So a lambda of 1.10 means that the population is increasing by 10% during that time step. Or if lambda is 0.98, it means that the population is decreasing by 2% in that time step. And I have to give a shout out to the professor that taught me population ecology a long time ago at the University of Montana, Dr. Scott Mills. So I sure hope this is review for most of y'all. But as a reminder, R is a little bit different than lambda. So R is the intrinsic or instantaneous rate of population growth calculated via calculus. So R is equivalent to the birth rate, the instantaneous birth rate minus the instantaneous death rate, the mortality rate. Or you can also calculate R by taking the natural log of lambda. So this equation is just saying the change in population abundance during this interval of time, during this change in time, is equal to R, the continuous, intrinsic, instantaneous rate of population growth, multiplied by the original population size. So remember, lambda is centered about 1, R is centered about 0. So if R is greater than 0, the population is increasing. If R equals 0, the population is replacing itself, it's stable. And an R less than 0 means the population is declining. Populations of all organisms have a great capacity for increase, perhaps best illustrated by us, the human population. So I was born in 1976, during which time the world had less than 4 billion people on the planet. Just in my lifetime, the population has doubled to 8 billion. We just hit 8 billion a few months ago. This is fall of 2022. So just in my 46 years, I have seen a doubling of the human population. We're likely to hit 11 to 13 billion Homo sapiens on planet Earth by the end of the century, assuming that we don't nuke ourselves and we can stabilize our climate. And that's pretty amazing, but also a little bit scary. But my point is that all mammal populations, even large-bodied mammalian populations like these African elephants, are capable of exponential or density-independent population growth. So this occurs under idealized conditions. That is to say, it's a perfect world for this species, and there are no limiting factors. Food is abundant, meaning there's plenty to eat for everyone in the population, and therefore all individuals within the population are reproducing at their physiological capacity. They're pumping out offspring as quickly as they can given their physiological constraints. So a great example, in Kruger National Park in South Africa, the park was first established at the beginning of the 20th century. By the time the park was established, the elephant population had just been decimated in Kruger by the ivory trade. In 1905, there were reported only 10 elephants within the park boundaries. But herein, this newly established Kruger National Park in South Africa, they were protected from hunting. And they had the whole park to themselves, lots of trees to eat, and no competition from other elephants. And so the population grew, slowly at first, right? Because elephants have a long generation time. Okay, so there's a lag here before we see in the 1960s this inflection and then this exponential population growth. So the population of elephants in Kruger National Park is going to go from 10 to almost 8,000 in about 60 years. Exponential population growth under idealized conditions. But populations of animals cannot increase indefinitely, especially large-bodied elephants that are destroying trees on the savannah. So populations of elephants are inexorably going to run out of food. The population is going to bump up against what's called its carrying capacity, which is denoted with a capital K. That is to say, the maximum population abundance of that species that environment can support. So I want you to recognize, though, that carrying capacity is not some golden magic fixed number. Carrying capacity is fluid. It can change from in one habitat from one year to the next. It's not static over time. So think about a really good monsoon rain season and the flush of high protein herbaceous material that follows. Or maybe the community's successional state. So if a fire has just ripped through there, it's going to alter the system's carrying capacity. And carrying capacity is not the same for a species from one habitat to the next. Okay? All that said, the logistic or density-dependent model of population growth is more appropriate for large-bodied mammals like elephants, and I'm going to introduce that to you here shortly because it's more realistic, because it's going to incorporate the carrying capacity of that environment for that population. So factors in nature that are going to keep populations from increasing indefinitely are traditionally divided into two types. There are factors that are density independent, as well as factors that depend upon the density of the population, considered density dependent factors. So let's start with density-independent factors. These are things like storms, fires, floods, abiotic events that simply don't care about the density of individuals within the population. It's going to kill individuals without regard to how many are present or their underlying nutritional condition. Density-dependent factors are things like food supply, shelter, those both of which are going to become scarce at high densities. Predators, which are more likely to switch their prey when their prey species reaches a higher density, and they're more likely to locate and capture them. Both parasites and disease are considered density-dependent factors because when you have high densities of organisms, that's going to increase transmission rates of both. In short, The effects of density-dependent factors on the population are stronger when the density is high and weaker when the density is low. Exponential population growth is a form of density-independent growth because the population does not slow with increasing number of animals. But the logistic or the density-dependent population growth model does. So let's cover that. In logistic or density-dependent population growth, we're going to see this sigmoidal, this S-shaped population growth model. So initially, the population is going to grow exponentially, just like before, until we hit this inflection point. So this is where the density-dependent effects kick in. So as you get more conspecifics on the landscape, it causes increased intraspecific competition, which may result in decreased birth rates, increased mortality rates, and then increased immigration rates. That is, individuals permanently leaving the population, or all of the above. And then the population growth rate, right, which is the slope of this line, is going to decrease and eventually flatten out. Population growth is going to stop when we bump up against big K, which is the ecological carrying capacity. So hopefully you can see it here on this graph on the far right. So this is the recruitment rate as a function of population size. Initially, as the population grows, the number of individuals recruited into the population, these are juveniles that move into the reproductively aged category of adults, that's going to increase until we hit that inflection point. And then at this point, the number of juveniles recruited into the adult population begins to decline until we hit carrying capacity, where there's no more new recruitment and population growth stops. Okay, so the term that's driving all of this is this term here in parentheses. So this is the density-dependent term. So essentially, when n is very small relative to k, when the population is very low, okay, this number is going to be close to 1, which means that essentially we're just looking at exponential growth. However, as population abundance increases relative to the carrying capacity, this number is going to approach 0. And when it hits 0, right, 0 in a numerator means that this term is 0. That means this entire right side of the equation is 0, which means that we've hit the asymptote. We've hit the carrying capacity here. If if this population exceeds carrying capacity, right, creating a negative term right here, then we're actually going to see a population decline. So maybe the population overshoots carrying capacity. This term becomes negative, and then it's going to dip down below carrying capacity. And we can actually see this kind of waggle as we move up and below around carrying capacity. So here's a great and a short Khan Academy video, I think, that's really going to cement this in your minds. It's going to demonstrate how 1,000 rabbits, an initial population abundance of just 1,000 rabbits growing at a 10% rate per time step will hit, get this, 93 million rabbits in just 120 time steps. So it's going to show you that exponential growth. It was declining calf elk recruitment as indexed by decades of spring green-up flight data in the Blackfoot Valley, Montana, that was the entire impetus for my master's research at the University of Montana between 2002 and 2005. So during this time, the gray wolf was recolonizing the area. Both mountain lion and bear populations, both black bear and grizzly bear populations, were increasing. And the elk herd in this hunting district had tripled in abundance since the early 1980s. So the Rocky Mountain Elk Foundation, Safari Club International, and the Boone and Crockett Club wanted to understand what was suppressing elk calf recruitment. Was elk recruitment being suppressed by top-down regulation via these increasing predator populations, or was recruitment being suppressed from the bottom up by high densities of elk that were in competition for limited forage during those long Montana winters? So that's my hook to get you to tune back in to Module 7 for your case study entitled The Impact of Variation in Calf Survival on Elk Population Dynamics in West Central Montana. I think it'll be an enjoyable one for you. And there's some great gory photos of calf elk that were killed by mountain lions and bears. So this is an information-dense table from your textbook. This is table 25.1. On the far left here are life history characteristics. So things like the nutritional condition of females, the pregnancy rate of yearlings, the body mass of newborns. And what this table is doing is formalizing the predictions, what we would expect to see with respect to these life history characteristics when population abundance is low relative to carrying capacity and when population abundance is at or near carrying capacity. So when we have high densities of ungulates, we would expect the nutritional condition of females to be quite poor. We would expect few yearlings to become pregnant. We would expect newborns to be born relatively lighter than when densities are low. So I'm showing you this table because we built something very, very similar as a way to structure our experimental design to test 3 different hypotheses that we thought were viable in explaining declining elk calf recruitment. So we're going to be coming back to this in the case study. But for now, what do I mean by life history traits? Life history traits include traits like size at birth, mean litter size, the age at reproductive maturity, the degree of parental care. These are traits that are going to directly influence fecundity, meaning the animal's reproductive output, as well as survival, meaning these are traits that are sculpted by natural selection. And as you know, natural selection is blind. It recognizes only one currency, and that is successful offspring. All that matters in evolutionary fitness is how many of your offspring reproduce themselves. How many of your young are going to pass along your genes. So different mammalian lineages have evolved different strategies to maximize their evolutionary fitness, different approaches to the amount of energy, relative energy, that we're going to allocate towards our own survival versus investing in our reproductive output at this time. RK selection strategy was coined by the famous ecologists Robert MacArthur and E.O. Wilson in their foundational publication in 1967, where they lay out their island biogeography framework. In short, our selected strategists are species that are going to live fast, die young, and pump out lots of babies. So they tend to be small-bodied organisms. They have short lifespans. They're going to grow rapidly and reach sexual maturity early. As soon as they sexually mature, they're going to pump out lots of babies as quickly as possible. They're going to put little energy into their young, and they're going to invest very little in parental care and protection. So they pump out so many babies that their offspring are considered cheap. They're expendable. Our selected species tend to be generalists. They tend to thrive in highly variable environments. They're good colonizers, and they tend to be low trophic level species, prey species. So when you think about our selected mammals, I want you to think about rabbits and rodents. Okay? Their populations tend to grow exponentially. Hence, they're considered our selected species, but their populations never really tend to be impacted by density-dependent factors because they never really approach carrying capacity. Whereas K-selected strategists are species whose populations tend to show that sigmoidal S-shaped logistic population growth model. Their populations are governed by density-dependent factors. They do bump up against their carrying capacity. So these are large-bodied mammals. They tend to have very long lives. They're slow to reach sexual maturity. When they do produce offspring, they have small litter sizes, and they're going to invest a lot of energy as well as parental care in their young. They tend to be found in stable, late successional stage environments. Oftentimes they're specialists, predators at high trophic levels, but they're not always predators. So think large-bodied mammals. So think elephants, red kangaroos, whales, and then primates. Great example of K-selected species. However, as is often the case in ecology, species aren't necessarily going to fit cleanly into one of just two discrete categories. So Wilson and MacArthur's RK selection strategies has been replaced or updated, if you will, by the slow, fast life history tempo continuum. So it's a spectrum, really, from R to K. As an example, if we look at just reproductive output, so oysters are going to pump out enough gametes to produce 500 million microscopic offspring, the vast majority of which are not going to survive. Similarly, tuna may fertilize 6,000 eggs, most of which are going to be gobbled up. One of the fastest tempoed mammals are the hares, which may produce upwards of 12 young per year. Remember, hares produce precocial young. They don't have much parental care beyond a lactational period, whereas a mountain lion is going to stay with her cubs for 2 years, and she's going to teach them how to hunt. So she's trading off her fecundity at the moment for investing energy in parental care, enhancing the probability that her current offspring will learn to hunt and thrive on their own. Chimpanzees are actually even slower than us. Mom is going to nurse her young for 5 years compared to just 3 years of lactation in humans. So this is from Pianka's foundational work. These are all mammals, and as you can see, as mammalian adult body mass increases on the x-axes of these top two graphs, the age at first reproduction, that is to say the age in which the mammal reaches sexual maturity, linearly increases. This is a high R-squared, 0.72. So 72% of the variability in the age at first reproduction in mammals is predicted by adult body mass. Similarly, larger bodied animals like elephants and killer whales, they tend to live longer. So female killer whales can live more than 50 years in the wild. So this is informative. If you're a mammal that reproduces early, so this is age at first reproduction, you have much larger litter sizes. So as an example, my students at EMCC, we raise rats because we have a whole bunch, an extensive snake collection, too many snakes. And so we have to feed all of those snakes. So we breed rodents in my lab. A female rat is going to become reproductively mature at just 8 weeks old, and then they'll regularly have litter sizes of over a dozen pinkies. Okay, so again, when age at first reproduction is early, we're going to produce more young. So this is an R selected, and then this is a K selected. This is a fast tempo, and this is a slow tempo species on this continuum. Much of life history theory examines trade-offs, particularly trade-offs between investing in reproduction right now versus investing in your own survival now. That way you can reproduce in the future. Long-lived species have evolved strategies for energy allocation to maximize their reproductive success over the course of their entire lifetime by placing greater emphasis on adult survival and less energy allocated on any one single reproductive event. So we saw this one cold, dry spring in Montana's Blackfoot Valley when cow elk were in such poor condition that they were abandoning their calves, presumably because they just couldn't produce enough milk to nourish them and survive themselves. We'll come back to that. Individuals may adopt a risk-sensitive allocation of resources to reproduction in which investment in reproduction varies among years to increase survival and allow for energy to be allocated for future attempts at reproduction when conditions are more favorable. So in other words, maybe we hold off on reproduction at this moment because conditions aren't really good. We focus on our own survival and we invest in reproduction later in life when conditions are more favorable. Of course, this isn't a conscious thought process. Mammals aren't doing any family planning. But this is the underlying selection that's occurring. Ultimately, as a result of this behavior, adult survival in ungulates is relatively stable, while other vital rates are far more variable in stochastic environments. And this is exactly what our meta-analysis of 40 different elk populations revealed. Adult elk survival is relatively fixed. It doesn't vary very much within a population or across populations. But calf survival is wildly variable across both time and space. Many large mammals, especially ungulates, have slow-paced life tempos, meaning they are density dependent in their life histories, and they exhibit characteristics like large body size, long lifespan, low adult mortality, delayed reproduction when conditions aren't good, high maternal investment in young, and highly variable survival rates of those young. So this is the big idea from our work in Montana. Because adult survival is somewhat buffered, it tends to be high and relatively stable, while survival of the young, particularly the very susceptible neonates, is highly variable from one year to the next. So what do wildlife managers need to hone in on? They need to estimate the survival and the recruitment rate of young, because that is the best indicator of population trajectories. And I'm going to empirically demonstrate that in the upcoming case study. Most mammal species like elk are Iteroparous, from the Latin itero, meaning to repeat. It's an iteration. That is, they're able to breed more than once during their lifetime. That said, some marsupial mice in the genus Antechinus, shown here, these guys are, of course, from Australia. They're going to reproduce only once during their entire lifetimes. These are what we call Big Bang breeders. So they're Semelparous, from the Latin word semel, meaning just once, and perio, meaning to beget offspring. So they're going to exert this huge effort during their one reproductive episode, and then they die. Semelparity seems to be favored when reproduction involves extensive preparation for breeding, or it may be favored when environmental conditions are quite ephemeral or uncertain. So when it's good, we want to have that big bang. Your chapter is going to conclude with a look at population cyclicity, which is pretty rare in nature. For a mammal to be considered to have a true population cycle, there has to be constant periods between the peaks in amplitude, so as shown here. So the constant period between these spikes in population abundance. Population cycles are not even known to occur in the southern hemisphere, at least they haven't been detected yet, or in the tropics. One of the better documented examples of a cyclic species, I mentioned them at the outset, is the Siberian brown lemming around Barrow, Alaska, which has this population cycle of approximately 4 years between peaks in their population amplitude. So during one of these increases, breeding starts in autumn, and then by spring there are large numbers of lemmings present. So here it looks like in 1960, upwards of over 200 lemmings per hectare. So just this incredible spike in population density, which is really important on these tundras, right? Because this flush of lemmings is going to feed weasels and Arctic foxes, snowy owls, right? However, during the summer, the population is then going to crash again to a low level, and it's going to remain at that low level for 1 to 3 years before peaking in amplitude again. The most spectacular example of a population cycle, and it is in every ecology textbook, but I still really want to cover it, is the snowshoe hare and the lynx population, predator-prey dynamic population cycle that occurs in boreal forests and the tundras of North America. So these hare and lynx population estimates go way back to the 1850s. So this is data that's generated. It reflects the record of pelts that are harvested by fur trappers and sold to the Hudson Bay Company. So that's where those data come from. But you can see each of these cycles is about 10 years in length. About every 10 years, we see this peak in snowshoe hare populations when all of these pelts were brought in by the hundreds of thousands. But what's so cool is the lynx population is very synchronized to its prey. So lynx are specialists. They're really focused on those snowshoe hares. And we see this lag, right? So the snowshoe hare population peaks, and then 1 to 2 years later, the lynx population peaks. And then as that hare population plummets, the lynx population is also going to plummet 1 to 2 years later. So the predator-prey population cycle of the snowshoe hare and the Canadian lynx. All right, so that wraps up lecture 7.1, which is chapter 25 in your textbook. Some really important ungulate life history publications here by Gaillard. Come back next time for some gruesome and very real photos of calf elk mortality scenes in your case study. Many thanks for your time.